Hello everyone, my name is Brian Huser and I work at the Swedish University of Agricultural Sciences in the Department of Aquatic Sciences and Assessment in Uppsala, Sweden. During this presentation, I will be discussing the use of aluminum salts for lake management and restoration in U.S. lakes. I'll cover some recent case studies, discuss how the results have been used to improve on current methods, and talk about what future needs exist to further improve on dosing methods and applications. First, a brief background on the use of aluminum. Aluminum salts, mainly aluminum sulfate or alum in the US, have been used for lake treatment since the 1970s. Initially, aluminum was mainly added to strip water column phosphorus and or phytoplankton, but the main goal of most treatments now is the reduction of internal phosphorus loading. Dosing was initially based on alkalinity, which can result in overdosing or more likely underdosing. Following this, internal phosphorus loading rates were used to develop doses, which was a step in the right direction, but still inadequate. Now we use the amount of mobile sediment phosphorus, which is mainly iron-bound, loosely sorbed, and pore water phosphorus. Even here, though, we still don't have it quite figured out. Ryden and Welch recommended an aluminum dosing based on mobile phosphorus with a ratio of aluminum to mobile phosphorus of approximately 100:1 to reduce all available mobile phosphorus. De Vicente et al., on the other hand, recommended a much lower aluminum dose relative to sediment mobile phosphorus, approximately 10:1. This reduces pore water phosphorus but limits the reduced binding efficiency caused by crystallization of the aluminum hydroxide mineral that forms after treatment. These two endpoints leave a large gap between doses that are probably required to achieve management goals. Aluminum applications have not advanced much over time, and these generally target areas with sediment rich in phosphorus. This can lead to excess aluminum accumulation, however, and lower binding efficiency, which I will discuss further on in the talk. Data availability is generally poor with respect to treated lakes. Not always, but surface water quality data are usually available, and sometimes water column profiles are there. Sediment, however, is rarely analyzed, especially shortly after treatment while floc saturation is still occurring. These long-term water quality data sets and short-term sediment analysis pre- and post-treatment are important to determine if the methods we now have are adequate or whether some refinement of these methods may be necessary. We'll discuss some of these studies in this talk and then relate them to some of the recent advances we've made in aluminum dosing and application to lakes. The first study I want to cover is the restoration of the Minneapolis chain of lakes in Minnesota, located in the large urban city of Minneapolis. This project received Clean Water Partnership project funding from the US EPA to improve water quality. The lakes running north to south, they're all interconnected and flow north to south, include Cedar Lake, Lake of the Isles, Lake Calhoun, and then Lake Harriet. Lake Harriet then feeds into the Minnehaha Creek, which eventually empties into the Mississippi River. The chain receives approximately 2 to 3 million visits every year, so it's a highly visible system. External best management practices were installed before or just after aluminum was applied to the lakes. These had varying effectiveness for external phosphorus reduction. I won't get into that in this talk. Water quality data for these lakes are available since roughly 1970. The first two treatments, Cedar Lake and Lake of the Isles, were designed based on internal phosphorus loading rates, whereas the second two treatments, Calhoun and Harriet, were dosed using a modified version of the Ryden and Welch mobile sediment phosphorus method. Okay, let's take a look at some data. Cedar Lake is a diamictic lake and has a residence time of about 4.5 years. 27 grams of aluminum per meter squared were added in late 1995 and early 1996. And again, this dose was based on internal phosphorus loading, not sediment phosphorus. But there was water quality improvement after treatment, and it was substantial, with total phosphorus and chlorophyll A dropping at roughly 50% and water clarity, as Secchi depth, SD here, increasing by about 50%. I should add that these comparisons are based on just the 5 years of data prior to treatment, and then from data including 1996 through 2005. Although here on this chart, it does appear that total phosphorus and chlorophyll A remain better than pre-treatment, and that's true. Water clarity has suffered in recent years, and I will cover that in a minute. Lake of the Isles is a different story and a typical low-dose treatment, a shallow lake with a low residence time, and on top of that, the lake only receives 10% of its total phosphorus load from internal loading processes. 18 grams of aluminum per meter squared were added to the lake, And during the first 5 years, the lake did show water quality improvement. But after these first 5 years, water quality was not significantly different than that from 5 years prior to treatment. And if we take a look at the Secchi depth values for both Cedar and Lake of the Isles, it's a bit easier to see the perceived longevity of the treatment. Again, 10 years approximately for Cedar Lake, and then 5 years for Lake of the Isles. And I should add that there was still substantial, I don't show it here, but there was still substantial mobile phosphorus in the sediment shortly after treatment. So let's take a look at what's going on underneath the surface in Cedar Lake. With all these data that we have, we were able to do this. This graph shows hypolimitic phosphorus concentrations prior to treatment, which would be this top line up here, and during the first 5 years after treatment, which is the bottom line here. Basically no internal loading here going on. And then the 5 years following that, a little bit the internal loading starting to come back, but it's still different than pre-treatment, statistically different than pre-treatment. And then finally this third line with the dots in the yellow, from 2007 to 2011, phosphorus values in the hypolimian, we can see that although the line is lower, it's due to a lower intercept. The slope actually isn't statistically different than the slope of the line for pre-treatment. So the net internal load is not statistically different than pre-treatment now. And that sort of matches up with the Secchi depth data, showing that the first 10 years of treatment were a success, and then the following 5 years after that, we sort of returned to pre-treatment values. So here we have water quality data for Lake Calhoun, fairly deep dimictic lake with a long residence time. 42 grams of aluminum per meter squared right in Lake 2001, with substantial improvement in water quality seen through the last year of this data set, so it's still ongoing. I should add that while mobile sediment phosphorus was used to develop the dose for Lake Calhoun, only 2/3 of that dose could be added due to cost constraints, so longevity will probably be affected here. And we have data for Lake Harriet, also fairly deep and dimictic. The same dose was applied, but only as was applied to Calhoun, but only to the littoral zone in this lake. This was done not to reduce internal phosphorus loading, but rather to limit migrating cyanobacteria from utilizing phosphorus near the sediment surface. But as I will show a few slides later, the treatment was not very effective in doing this. Water quality did improve, however, for about 5 years after treatment, but then returned to pre-treatment values. And the dose, although based on mobile phosphorus, was more similar to the dose added to Lake of the Isles when considering the entire lake area. Let's take a look at the bottom water phosphorus in Lake Calhoun and see if we can find out what's driving the improved water quality. Internal phosphorus loading remains reduced 11 years after treatment. The top line here again are the pre-treatment values, phosphorus in the hypolimian approximately reaching 400 micrograms per liter. Actually, that's a 10-year average pre-treatment, so sometimes it was above 400, sometimes a little bit less. Following treatment, actually the first 2 years, it appeared that internal loading might even be negative. Phosphorus values in the hypolimian were lower than in the epilimian. But at any rate, for the first 5 years, there's limited to no loading. The next 5 years, we see a slight increase, but it's been fairly consistent. The maximum concentration of the hypolimian has been around 100 micrograms per liter during the last 5 years here in this data set. Back to Lake Harriet, we can see why the littoral application was only somewhat effective for reducing phosphorus availability to migrating cyanobacteria. Within just a few months, the aluminum and the phosphorus bound to it drifted to the center of the lake. So the two figures I show at the bottom here represent sediment phosphorus data from 4 meters here on the left, and then 25 meters here on the right. I should mention that all phosphorus fractions were extracted according to the modified center et al. Scheme that I believe Casper mentioned in his opening talk. At 4 meters, we can see how aluminum-bound phosphorus in red was initially elevated after treatment. The dashed line here shows treatment, but then decreased to pre-treatment values just 2.5 months after treatment. And where did it go? Well, if we look at the graph on the right here, we can see that aluminum-bound phosphorus is increasing at the 25-meter water column depth. So the aluminum and the aluminum-bound phosphorus basically were translocated to the deeper part of the lake. And what's also interesting about these data is that mobile phosphorus in 2011 at 25 meters is similar to pre-treatment. And this fits well with the water quality data we have. So the aluminum treatment here, initially designed as a littoral treatment, ended up drifting to the deeper areas of the lake. The reduction in internal loading was either caused by binding of organic rich sediment in shallow areas that would have normally been moved deeper to deeper areas of the lake naturally, or the aluminum still had binding capacity as it moved, resulting in conversion of mobile phosphorus in deeper areas to aluminum-bound phosphorus. This, we don't really know this at this point, but it's interesting to note here that the binding ratios in the sediment 10 years after treatment were around 2:1 aluminum to aluminum-bound phosphorus formed. And this is basically 2 units of aluminum to bind one unit of phosphorus. And these are some of the lowest ratios detected for aluminum-treated lakes and indicate very good binding efficiency between aluminum and phosphorus. Another study I would like to talk about briefly is Kohlman Lake, a shallow lake with a mean depth of about 1 meter located in St. Paul, Minnesota. This lake received a split treatment with combined alum and sodium aluminate, a buffered aluminum compound. Carp exposures were installed just after treatment, and sediment cores were collected pre and post treatment. And the idea here was to use aluminum as a conservative tracer of mixing depth of sediment in the lake. The experiment lasted about 4.5 months, and the added aluminum again was used to estimate sediment mixing depth. And the graph here shows the average depth of aluminum penetration into the sediment in the exclosures here, and at 3 other sites within the lake where carp were known to congregate according to radio tracking. As we can see on the graph, there's a substantial increase in sediment mixing depth caused by carp, almost a 3-fold increase. And because the original aluminum dose in this lake was based on only 6 centimeter sediment mixing depth, the longevity of this treatment may be affected. Here in the exclosures, we have a mixing depth of approximately 5 centimeters, but in the rest of the lake, it's closer to 14. So that could be a problem, especially if we look at the amount of phosphorus in the sediment. For this graph, I just want to quickly point out that mobile phosphorus mass content in the sediment increases between 2 and 3 times in Kohlman Lake, depending on location, when comparing total mass of phosphorus at 4 centimeters and then 14 centimeters sediment depth. We have 3 different core locations where we analyze phosphorus here, and you can see the sharp increase as you increase sediment depth. So the total amount of phosphorus is increasing. This is just mobile phosphorus, and we don't include the mineralization of organic matter, and this is likely to increase with sediment mixing, further increasing the amount of phosphorus potentially available to the water column. Okay, let's move on and talk a bit about dosing. Because the available methods for aluminum dosing are still somewhat rigid and provide only a low dose to avoid aging effects, or a high dose that may exceed the amount of aluminum required to achieve water quality goals, we're in the process of developing our own dynamic model for determining aluminum dose. I use air quotes for dynamic because the model itself is based on empirical data from roughly 20 lakes and between 300 and 400 aluminum additions to sediment. The model itself, however, gives the user a flexible method to determine aluminum dose required to achieve internal phosphorus loading goals directly after treatment. By the way, if anyone can come up with a better name for the model, it's the ALMO-P model, feel free to let me know. We aren't exactly happy with the current one. So the figure on the right here, it looks pretty green, although it's more of a color when you're out on the lake. This is a Secchi disc resting on the bottom of the lake we recently treated using this ALMO-P model. And this is 11 meters you're seeing down into the water column. Hopefully you can see that picture there. Well, here we see why I used the term dynamic on the previous slide. Using the ALMO-P model, we can calculate the amount of aluminum-bound phosphorus formed after an addition of a certain amount of aluminum, and then we can also calculate the decrease in mobile phosphorus. Here on this graph to the right, we have sediment phosphorus mass on the left, and then in essence aluminum added to the sediment on the right. And you can see an increase in the aluminum-bound phosphorus and a subsequent decrease in mobile phosphorus because it's being converted to aluminum-bound phosphorus. Now, we've also connected these results to the internal phosphorus loading rate model developed by Pilgrim et al., which is a a linear model which relates mobile sediment phosphorus concentrations to internal phosphorus loading rate of inorganic phosphorus. And that's the dashed line here, and you can see it matching up pretty well with the mobile phosphorus, and the scale is on the right here, the rate scale. Now, for example, if the loading rate target is not exactly on one of the points output from the ALMOP model, that's what these points represent. So we get 2, 4, 6 points, and 7 if you include 0. But I don't think we should include that. So you get these points here and a distribution of changes in aluminum bound phosphorus and mobile phosphorus. But if your treatment dose or your internal loading goal doesn't fit quite on one of these points, you can either interpolate between these points, or as I've done here, you can use a more rigorous solution like the Langmuir model to develop the dosing curve using the model output from the ALMOP model. Okay, let's say we've run the model and we have a dose for our lake. How do we know if we might be adding too much aluminum with respect to crystallization now and reduce binding efficiency? This is important to consider if we want to convert the highest amount of phosphorus possible to aluminum-bound phosphorus. Well, one thing we can do is to take a look at the lake morphology and total aluminum dose added to the lake. We've developed a model that shows that binding efficiency of aluminum is related to how much aluminum you add to the lake and the approximate slope of the sediment surface. And that's the solution up here. It's just the ratio of aluminum to phosphorus bound to aluminum versus the aluminum depth index, which is just an estimate of slope, and total aluminum dose. If the slope is steep, translocation of the aluminum flock is likely to occur, as we saw in Lake Harriet, and we will end up with excess flock in deeper areas of the lake. This excess flock will start to crystallize in the absence of phosphorus, thereby lowering binding efficiency and increasing the aluminum to aluminum bound phosphorus ratio. We can see this in the figure on the left, where the aluminum to aluminum bound phosphorus ratio increases as the aluminum depth index or sediment slope of the lake increases. This equation up here on top can be rewritten to solve for aluminum dose required to reach a desired binding efficiency or aluminum to aluminum bound phosphorus ratio. And this is what was done in the second figure here, where we modeled aluminum dose limits based on different core depths, although I have mean depth here, but it should be core depth. And then lake areas to achieve a final aluminum to aluminum bound phosphorus form ratio of 10. It's important to note here that this study was based on 7 lakes, 8 cores in total, in a small geographic area. And these were mostly bowl-shaped glacial kettle lakes, so the results may not be applicable to other systems, especially those with variable morphology. But it's a starting point anyway, and should give a rough idea if an aluminum dose may be less effective than desired. If this occurs, splitting the dose over a number of years is a common solution. More work is needed in this area, however, to help elucidate factors that can affect the efficiency of binding between aluminum and phosphorus. Now, we've used these methods to treat a number of lakes now, and here I want to briefly present the results from Lake Rebecca, also in Minnesota. 81 grams of aluminum per meter squared were added over 2 treatments, so this is a split treatment. The decrease in mobile phosphorus and increase in aluminum-bound phosphorus can be seen here, and it's pretty substantial in what we expected. So the dashed lines represent pre-treatment concentrations of phosphorus, and the solid lines represent post-treatment. You can see the decrease in mobile phosphorus as it's being converted to aluminum-bound phosphorus there on the graph on the right. And the internal loading in this lake post-treatment has been around 0, and the dosing ratio was approximately 100 to 1 as aluminum to aluminum-bound phosphorus. But the doses we've seen generally aren't this high and range from ratios of 30 to 60, depending on desired internal loading reductions. So what does all this mean for aluminum salt application to lakes? First, large doses should be split over a number of years to improve binding efficiency between aluminum and phosphorus. Another benefit to dose splitting is cost savings when lake buffering capacity is limited. Another change is to apply an aluminum dose evenly across the lake. This is a little more iffy, but instead of adding all the aluminum to targeted high phosphorus areas, we spread the dose out. And the results from Lake Harriet showed that the aluminum from treatment did move to deep areas of the lake and limit internal phosphorus loading, even though it was applied to the littoral zone. Binding efficiency was also very high in this case. We still have questions though, such as how long to wait between split applications. Monitoring water quality and or sediments will give clues as to when a follow-up treatment could be added, but this is more of a wait and see method. So I know a few people are currently working on estimating longevity of alumina treatments. We are too, but it's still a work in progress, and definitely further research and experiments are warranted in this area. Now, there are a number of other considerations and future needs with respect to dosing of aluminum. Organic phosphorus is still somewhat problematic. We can estimate expected degradation rates of certain forms, but in order to properly add enough aluminum, additional sediment tests are needed, increasing treatment costs. And even if one estimates the potential organic phosphorus contribution, adding enough aluminum to cover this pool of phosphorus may result in lower binding efficiency if this added aluminum begins to crystallize, but phosphorus is released from the organic matter, and binding between aluminum and phosphorus can occur. The active sediment layer, which is needed to estimate the total phosphorus available for release, can be difficult to determine, especially in systems with benthivorous fish species, as we saw in Kohlman Lake. We also need to better define the relationship between binding efficiency and internal phosphorus loading reduction after treatment. This will likely involve some type of cost-benefit analysis. And finally, we need more post and pre-treatment data, especially in cases where doses have been calculated using newer methods based on mobile sediment phosphorus. We now have ratios of aluminum to aluminum-bound phosphorus ranging from 7 to approximately 150 just a year or two after treatment in these lakes. They're all over the board. As I've shown here, yeah, they are all over the board. But what will they be after the aluminum hydroxide layer has been or hasn't been saturated with phosphorus? We just don't know this, but it's obviously important information to have. So in summary, a more dynamic aluminum dosing model provides a flexible way to calculate aluminum doses to reduce internal phosphorus loading in lakes, but more work is needed to balance the initial treatment results with treatment cost and longevity. Higher doses may need to be split and or applied over the entire lake area to improve binding efficiency. Here we need better methods to estimate a timeline that maximizes treatment benefit. Organic phosphorus remains difficult to deal with without a detailed analysis of sediment. Development of dosing methods that adequately incorporate this phosphorus pool and degradation rates are needed. And finally, more work is needed to estimate longevity treatments. I think this is the most important part here, especially in urban areas where it is difficult to reduce external phosphorus loads. Thank you very much for taking the time to listen to my talk.